We investigate ensembling with deep generative views for classification tasks. Many learning-based vision problems rely on image datasets, but images are only discrete snapshots of the underlying continuous world. Recently, GANs have shown the ability to approximate the continuous image manifold. We investigate using these image variations for ensembling and classification. In standard classification, an image is fed through a classifier network to yield a prediction. Here, we generate additional variations of the input image using a GAN, classify each, and ensemble the results. But how do we obtain these GAN-generated variations? The first step of our pipeline is to project the image into the latent space of a pre-trained GAN. Following current best practices, we center the image and use an encoder network to get an initial guess of the latent code. We then perform a secondary optimization step, which allows us to better match the input image. With the optimized latent code W star, we can now perturb it to get meaningful variations. We investigate 3 different ways we can perturb the optimized latent code. The style mixing operation takes the optimized latent code and a completely random latent code and swaps them at a specified layer of StyleGAN. We also tried isotropic perturbations and using PCA directions, but we found that style mixing was more beneficial across different experiment settings. We start with the StyleGAN face generator combined with celeb A HQ attributes as a binary classification task. To visualize the qualitative output, we first obtain the GAN reconstruction of the image. When we perform style mixing in the coarse layers, this causes shape changes in the output, while style mixing in the fine layers changes the coloring of the output. For quantitative comparisons, we first measure the standard test accuracy of a trained classifier. However, when we project the input image through the GAN and ensemble the GAN-generated variants, we found that in some cases, it can actually do worse compared to classifying the image itself due to imperfections in GAN reconstructions. So we use a soft weighting to balance between the original image and the GAN variants. We find that an intermediate weight often does better than either extreme. Next, we'll investigate how the GAN-generated images compare to traditional test time ensembling methods such as cropping. We compute the change in classification accuracy when using a single test image compared to ensemble of color jittered images or cropped images. Ensembling small spatial crops improves classification accuracy. Using the GAN-generated style mixing ensembles performs similarly to ensembled crops. However, when averaged over the 40 facial attributes, the benefits are greater when both are combined together. Moving on from facial attributes, we experiment with a 3-way car classification task. Classifying image crops directly yields 96.6% accuracy. Fine layer style mixing works best in the ensemble, and without training the classifier on GAN images, there is a small increase in accuracy over ensembling crops alone. Since these reconstructions may not exactly match the input images, we also try fine-tuning the classifier on GAN reconstructions. The benefit to test time ensembling with GAN outputs improves when the classifier is fine-tuned on these reconstructions or on perturbed GAN images using the style mixing operation. We next try a more difficult CAT classification task with 12 categories. Coarse layer style mixing worked better here, but fine-tuning the classifier was necessary to achieve a performance boost. Through our experiments, we found that there are some key requirements for GAN-based ensembling. First, the GAN must be able to model the target domain well to preserve details for classification. Next, finding the latent code corresponding to a real image can be expensive, and there is a trade-off between optimization time and reconstruction quality. Finally, the classifier tends to be quite sensitive to GAN artifacts, thus requiring a soft ensembling weight. Taken together, we find that the benefits to test time ensembling with GAN views is currently limited to relatively simple tasks with small structured data sets. But as generation and inversion technology improves, similar ensembling techniques may yield more benefits in the future. To summarize, we use the StyleGAN generator as a source of emergent image variations. We project an image into the generator's latent space, perturb the latent code, and ensemble these variations together at test time. However, due to imperfections in the GAN reconstruction, we need to adjust the ensembling procedures. Thanks for listening, and please check out our project website or poster session for more details.